Good day, and welcome back for part one of our discussion on limits at infinity. So, just to give you a reminder, our short term goal is to use properties of calculus and also some previous algebra or pre calculus ideas or techniques to sketch accurate graphs of a function, which we will get to in our next section. And we already began this investigation in our previous section when we explored how the derivative affects the shape of a graph. Recall, for example, that when the first derivative is positive, a function is increasing. When it's negative, the function is decreasing. And the second derivative tells us something about the concavity of the curve. And if we happen to have a little more information, say maybe the locations and points corresponding to local maxes and mins, maybe a few roots or x-intercepts of the polynomial, we can give a very accurate sketch of what's going on in the middle of the graph. But what that leaves up to interpretation is what's happening way off to the right or way off to the left, which is another way of saying what is the limit as we approach infinity of the curve. And just to get us thinking along those lines, let me begin with a motivating example. In red, we have the graph of the curve y equals f of x. And the question that we might want to ask is, what is happening to the values of this function way to the right, that is as x approaches infinity, or way to the left, which would be asking as x approaches minus infinity. So in this case, I think very intuitively we can say that when we substitute in large values of x to our function, those outputs appear to be getting very close to that black dashed line, which corresponds to a y value or an output of 3. Similarly, if we plug in very large but negative inputs for x, we can see very intuitively once again that our function values are getting very, very small and they appear to be approaching 0. And this is precisely how we can think of the limits of a function as we approach plus or minus infinity. So let's go ahead and be a bit more precise in terms of how we can define this concept. In this case, we would say the limit as x approaches infinity of a function is the number L, and what that means is that the function values or outputs of f of x can be made as close as we like to L by making that input large. So it's very similar to that idea we had of a limit previously. It's just now we have to change our interpretation a bit by saying that for a large input, the function output is close to L. And note, there's nothing special about defining this limit as x approaches infinity. We just as easily could have instead defined the limit as x approaches minus infinity of the function. And so that limit is equal to L if we can make the outputs as close as we would like to L by making those inputs x sufficiently large, and because we're approaching negative infinity, it would be large negative inputs to the function. And let me give a graphical illustration of what we should expect to see with limits at infinity. And of course, the key idea, at least from an intuitive perspective, is as we get far enough out to the right, i.e. large inputs, the function values are going to be coming close to this dashed horizontal line. In our motivating example, we saw that occur with the function approaching the line from below. But I just want to note there's many different ways the function or the curve could approach that, what we will call horizontal asymptote. It could definitely approach it from above. But at the same time, just a reminder from our previous experience with these, once again, I'll say horizontal asymptotes, it's perfectly fine to have a curve which crosses over just as long as you're eventually becoming close to that line. And in either case, note this black dashed line would be represented by y equals L. In this line, y equals L plays an important role, and it is called a horizontal asymptote. And I will almost always abbreviate horizontal asymptote as simply capital H, capital A. And of course, you're more than welcome to do the same. And note that y equals L is called a horizontal asymptote whenever L is the limit as x approaches, and note it could be plus or minus infinity of the function f of x. And one thing that I want to really emphasize is that a horizontal asymptote is a line. A very common and even subtle mistake is when you are asked to find a horizontal asymptote, you tell me a number. So it is an incorrect statement to say that L is a horizontal asymptote of the function. It is a correct statement to say the line y equals L is a horizontal asymptote of the function. So be warned, you need to be a bit careful with how you present your horizontal asymptote. It's not a number, it's a line. Also, something I would like you to think about very briefly, how many horizontal asymptotes can a function have? And it turns out a function can have what? 0 horizontal asymptotes, 1, or at most 2 horizontal asymptotes. And from a graphical perspective, a case where something has more than 1 horizontal asymptote would be to go back to this previous example that we started with and note that this is a graph of a function with 2 horizontal asymptotes. Corresponding to the limit at infinity, we would have a horizontal asymptote y equals 3, and corresponding to the limit at minus infinity, we would have a second horizontal asymptote of y equals 0. So note in this motivating example, there are 2 horizontal asymptotes, y equals 3, note that's a line, and y equals 0. And let's finish this introduction to limits at infinity with a nice concrete example. Let's graph the curve given by the function 1 over x and just graphically determine the limits as we approach plus or minus infinity. The graph of f equals 1 over x, the reciprocal function, is something that we should have some familiarity with. Roughly speaking, it's going to look something like this. So it has this vertical asymptote corresponding to the line x equals 0, and we'll talk a little bit more about vertical asymptotes in our next section. And we can very clearly see graphically now what the horizontal asymptotes are going to be. So pause the video and maybe just write down underneath what is or are the horizontal asymptotes. So in this case, we can see that as we approach plus or minus infinity, the curve is very clearly approaching that x-axis. And intuitively, this makes a lot of sense. When you divide by a big number, you get back something small. So think 1 over 10, 1 over 100, 1 over 1,000, 1 over 1,000,000, and so on. Dividing by a big number is going to give you back something small. So as we approach infinity, 1 over x has outputs that are arbitrarily small. As we approach minus infinity, it has outputs that are arbitrary small and negative. So it's approaching 0 from below. That gives us a single horizontal asymptote, the line y equals 0. And it turns out that there's really nothing special about having the function 1 over x. If we had 1 over x raised to a positive power, the exact same observation could be made, and that will be a new limit law for us that we will use to start our next video. So stay tuned and take care.